Morning, my dear students. Welcome to this session on cables, effect of temperature on cables we are talking about. So last session, what is required for this effect of temperature on cables, on cable tension, is started with finding the cable length, right? What is required here is cable length, that is S is required. So how you calculate, because we will not be given the value of S. What you will be given, or you will know in the question, or practically, even practically also, that the distance between the supports you are able to measure, and the sag value of the lowest point or something, you can measure it with the latest equipment of the surveying, where the levels or the coordinates of the point are can be easily measured with total station and the latest technology available in surveying. Okay, so if you have 2 points, you can measure the distance between 2 points just by knowing the coordinates of the points from the total station, and also the elevation. Okay, so total station will give you the coordinates, longitudes and latitudes of the points on earth. Okay, so for that matter, of any point, right? So that's way uh, that way you can know the L value, you can get it, and H value you can get it. So with these two known values, so you need to have a formula or expression, mathematical expression, to find S. So that is found in the last session. So S is equal to L into 1 plus 8 by 3 H by L whole square, or H square by L square. Okay. Right. Now proceeding further to see what is the effect of temperature on cables. Right. We start with the cable length. Let us say, the change in cable length. That means infinitely small change, ds, what we call, is equal to, okay. So this is constant term, right? So there is no change, zero. Change is zero. At 8 into h square will become 2h into change in that infinitely small change in h. Okay, change in h happens. H will change, right? So it will become dh divided by 3l. L is constant again. So first term, as this is constant, so differential value of constant is 0. So now you are differentiating. So it will be easy for you if I talk like differentiation. So partially differentiate left hand side and partially differentiate right hand side. So this is 0 because it is a constant. So H is a variable. When temperature changes, H will change, S will change, whereas L is constant. So 2H dH. And now, so ds is equal to 16H by 3L into no dH. So I am converting this infinitely small change into delta, the change in dimension. Okay, change in uh, uh, cable length, change in sag value, right? Because we have worked out in strength of materials, if you remember. So what is the change in length because of temperature? It is delta L is equal to L alpha T. The same you can use it here. So delta S is equal to S into alpha into T. So what is S you will substitute now? L plus 8h square by 3L, right? So alpha into T will be outside. Right. Now you send alpha into T inside. So it will be L alpha T plus the other term like alpha into T into 8h square by 3L is having a negligible value, right? So H square H by L itself is a negligible value because L will be of 100 meters or so practically. So H will be maybe 2 or 3 meters. So H by L value itself is a negligible value, and square of H by L is much more negligible value, right? So that's why. So this second term we are neglecting, so it is negligible value, right? So negligible, okay, right, right. So what is on the left hand side, what is on the right hand side? Okay, so delta S is equal to S alpha T. We have written S is substituted for S. What is S I have substituted into alpha T. So L alpha T thus become L alpha T, and the second term we are neglect. So delta S finally you can write it as L alpha T. What is delta S? Substitute this one. So delta H into 16H by 3L is equal to L alpha T. Now finally, what is delta H? Change in sag is equal to delta H. 3L goes to the numerator and 16H comes to this will be reversed. So 3L by 16H into L alpha T. So this is a change in sag, right? So once you get change in sag, okay, this is one requirement, okay, got it, right? So change in cable length and change in sag, okay. So once you get change in sag, you can see all these quantities, you can get it. L is a given data, H is a given data, alpha is given data for the material, temperature change you can it will be a given data. So delta H you can get it. So once you get delta H, substitute it here, get change in cable length. Okay. So that is all about geometric quantities. Change in geometric quantities. What happens when temperature changes? So when temperature is changed, cable length is going to change. That means delta S. And sag also is going to change. That is delta H. So we have expressions for both. Now, if the S and H are changed, automatically the forces also will change. Okay. So how do you find that? From general cable theorem, so horizontal cable tension into the sag value is equal to moment at center. So we are considering or we are applying the general cable theorem at center. Okay, so this is the center point. So we are applying the cable theorem at this point. So this is H, horizontal cable tension, and this is H. So H multiplied by Y is equal to H for center. So this is point C, moment at C, equal to moment at C. Right. So what is H is equal to MC divided by H. Okay. So now partially differentiate both sides, right, with respect to H. So DH, D capital H means force, right? Horizontal cable tension divided by small dh is equal to D by So I'm doing dy dh on both sides. So dy dh of mc divided by h. mc is constant. Okay, so 1 by h differentiation minus 1 by h square. Okay, so 1 by h differentiation. What it is? H power minus 1. Okay, so it will be h power minus 2. Okay, so what happens? H power minus 2, I can write 1 by h square, right? So that is the differentiation value. So minus 1 into h power minus 2 is the differentiation value. So what you can write for this? Minus 1 by h square. So that is this one. So dh by small dh, okay, is equal to minus mc by h square. I am writing h into 1 by h. Okay. So now you just rearrange the terms. Okay. So what is mc by h? Is capital H. So replace this term with capital H. So it is minus capital H by small h. Left hand side is same, d capital H by d small h. Okay. Right. So just send this term here and take this small dh there. So that will give you this term. Okay. Right. So d capital H divided by capital H is equal to minus. Don't forget minus sign. So small d small h by h. Okay. Right. Now again same concept. Differentiation is changed to deformation quantity delta. So we want change in values. Okay. So I mean delta h by h is equal to minus delta small h by h. So what we want is, we know already how to calculate delta H. Now what we want is change in tension value, change in cable tension. So that we will find out from this expression, right? So delta H divided by H is equal to minus, what is delta small h, you substitute 3L by 16H into L minus L alpha T, negative sign is there, and 1 by h, so into h already there, h square. So this is delta h by h expression. And finally, if you want delta h, send this h to the numerator. So that is the final expression. So change in cable tension, that means horizontal cable tension component of horizontal component of cable tension. Vertical components will never change. They will only be affected by the forces, the applied forces. Okay, so delta H will change. So that is 3L divided by 16H square L alpha T into H. Okay, so if you observe this one, why negative sign is there? Temperature increases. As the temperature increases, the horizontal component of cable tension decreases. That is why there is a negative sign, decrease symbol. Okay. So H final, H final is equal to, means after temperature change. So H initial plus delta H, right? Change value. So initial plus change. So as change, when the temperature is increased, H initial minus the value, you are getting a negative value. So H final is reduced, right? Decreases. What is the reason for that? What happens when temperature is increased? Okay, so we have talked about this. I'll tell you again. So let us imagine that this is the cable profile before temperature change. Let me just clear that. So you have to understand what is going to happen for cable if the right. Imagine temperature is increased. T we are increasing. What happens? Cable will elongate, right? Okay. Right, okay. Okay, so what is the tensile force direction when temperature is not increased? You draw the tangent for this cable at this point, right? We will draw a tangent for this. So this is the T direction, right? What happened after temperature is increased? When temperature is increased, cable elongated, and now the tangent for that cable is this much. This means what? Cable tension rotated clockwise. Rotated clockwise. So what? Okay. So what happened? So this is the horizontal reaction and vertical reaction. Let us say. So how you find t value just by the resultant, right? I think you remember this diagram from your engineering mechanics. Okay, so this is t value, right? So if this rotates clockwise, what happens? What happens? H is reduced, right? V anyhow is increased, right? So H is reduced. That is what we are calling it. H final is decreasing. Horizontal component of cable tension decreases. This is the reason. Okay, right. The other case, if the temperature, as the temperature of the cable decreases, horizontal component of cable tension increases. That also can be explained like this. Same way. So there is a cable, right? So before the reduction in cable tension, let us say this is the profile. So once you reduce the temperature, the profile is going to be like this. So what happens? This is the tensile force before temperature reduction. So after temperature is reduced, this is the tension. What happens? Tensile force rotated anti-clockwise. Okay, the tensile force rotation is anti-clockwise. Now this is H and this is V. So if the tensile force rotated anti-clockwise, means this is the rotation. What happens? H shall increase and V shall reduce. Then only it is possible, right? That arrow, if it is rotating like this, V shall reduce, H shall increase. Then only this line is possible for rotation. So that's why H is increased. H is increased. Okay. So temperature, if temperature is reduced, H will increase. Opposite relation. Okay. Horizontal cable tension will increase. Okay. So this is the complete information regarding temperature effect on cables. Okay. So how you do it? First, let us start with the cable length. Cable length. Then go for partial differentiation. Then convert that into deformable quantities, deformations. Then take the uh, strength of materials relation, like any member, if the temperature is increased or temperature is changed, what will be change in dimension? This is change in dimension. Then convert that into a simple form by neglecting the higher order terms or negligible terms. So finally, delta S, you can write it as L alpha T. So delta S already derived an expression. Substitute that, you will get delta H expression. Okay. Uh, from this relation, you can't get any value because both are unknowns. Only H value is known, L is known. Whereas if by converting like this, you are able to find delta H value because you know all these things. L, H, alpha, T, all these are known values, or you can measure it or will be a given data. Okay, so delta H, once you get it, then you can get delta S. Then from the cable theorem, general cable theorem, you can establish a relation for delta H finally. Okay, so closely follow this. And finally, after getting the formula, right, you should understand the behavior also. Okay, so why it is happening, right? So change in horizontal component of the cable tension can be found from this formula. So once you know H value, right, from the loads given, so now you apply temperature change. So 3L alpha T by 16H square into H. So this is how you can find the delta H value. Okay, right. Okay, thank you.